Well, here in podcast number 2, we are going to calculate, right, the pH of a solution, the pOH of a solution, the H plus, and the OH of a solution. The good news is if we can find one of these 4 things, we can actually use that one to find the other 3. So once we know one, we actually are going to be able to know all 4 of them. Well then, let's define what a pH of a solution is, right? And so one way that I kind of think about pH is just the power of the hydrogen ion. All right, that's not what it actually stands for. It's just kind of like, a jokey way of thinking about what it is. All right, when we see any equation that has a lowercase p in front of something, all right, mathematically, that is telling us to take the negative log of whatever basically is following it. So that p is telling us to take the negative log of something mathematically. All right, so in this case, we're going to take the negative log of our H plus concentration. All right, another way of doing this, right, is we can work backwards. And I could find the H plus concentration by taking the anti-log of the negative pH. All right, and that is 10 to the negative pH. All right, do not put 10 in your calculator and then raise it to the negative pH. There is a button that will look something like 10 to the X. Use that button to do this. You're going to hit 10 to the X thing. You're going to hit that and then put in the negative pH. All right, so don't just put in 10. It does not calculate it the same way. They are not the same thing, the way that your calculator reads things. All right, the higher the pH, the less acidic the solution is. And another way of saying that is the more basic. The lower the pH, the more acidic our solution is, right, or the less basic. All right, notice that when you see pH scales are generally going to go from 0 to 14. But I want you to know you can have negative pHs. You can have pHs greater than 14. It's just that most of the things that we come across in our daily lives are somewhere in between 0 and 14, and so thus we just kind of use this as our scale. But don't get caught up on, oh, it has to be somewhere in there. We're going to work a sample problem where we're going to have a negative pH. That's okay. So just don't freak out about it if you get a value that's outside that range. All right, notice that neutral has a pH of 7. All right, that is when we have our H plus concentration is equal to, right, 1 times 10 to the minus 7th. We learned that. And so the negative log of 1 times 10 to the minus 7th is 7. All right, hey, look at that. All right, that gives us that neutral thing. Well, if we know pH, then let's also talk about something that we're going to call pOH. And so pOH, again, right, notice that we have that P out in front. And so that's telling us to take the negative log of basically what follows it. And so we're going to take the negative log of the OH. That'll give us the pOH. And the same way, if we wanted to get the OH from the pOH, we could do the anti-log, or 10 to the negative pOH. Again, that is not just typing in 10 on our calculator. Also there on the bottom, right, we know we should have learned this one before, right? This is our H plus times our OH is equal to KW. All right, but also we know that the relationship between pH and pOH, pH plus pOH is equal to 14. So using all of this, if we know one of these values, we are going to be able to find all of those values. And that's something else that we're going to do as a sample problem. We're going to be able to do that soon. If we go back and remember some of the stuff that we learned from Chem 1, one of those things is that we have 7 strong acids. There's one more strong acid not listed here. You need to memorize those 7 strong acids. All right, I promise you that if you memorize those 7 strong acids, it's going to make your life a heck of a lot easier when it comes to a lot of things, not only just in this chapter, but in other chapters the rest of the way. Because if you know the 7 strong acids, then you know that any other acid has to be a weak acid. All right, so just memorize those 7 and you'll get them out of the way. Now recall that our strong acids completely ionize or separate out into their ions in solution. And if we have a monoprotic acid, right, those are the ones that have 1 proton out in front, right, like HCl, HBr, HR, HClO4, right, those are monoprotic acid, then our H plus concentration is equal to, right, whatever the concentration of the starting acid was. If you have a diprotic acid, like our H2SO4, then the H plus concentration will be equal to 2 times the concentration of the original acid. Right? Pretty easy to do, right? Because they're completely separating out. Just like for our strong acids, our strong bases, those are things that completely ionize as well. And when they completely ionize, they are going to produce OHs. All right, now again, right, these ones are going to produce 1 OH for every molecule. These ones are going to produce 2. All right, your strong bases are relatively easy to memorize as well. They're going to be group 1 or 2 metals plus some hydroxides attached to them. Like lithium is a group 1 metal, and it's got a hydroxide. Calcium is a group 2 metal, and you've got it paired up with some hydroxide. There. All right, if we wanted to then figure out the, say, the pOH and the pH of something here, notice that down here I've got, say, for a 0.1 molar solution of NaOH, then we have a 0.1 moles per liter of the OH, right, because it's completely ionizing. And so the pOH is the negative log of 0.1, right? That was that value. That gives us 1. And the pH, well, we know that the pH plus the pOH is equal to 14. So 14 is equal to 1.0 plus the pH. So the pH had to have been 13. Well, let's work sample problem 18-2, which we're going to find the H plus concentration and the pH, right? Once we find one of the 4 things, we could find all of them. In this case, we just need 2. It gives us that we have a volume and we have a mass percent. All right, now, this probably has been a while, but when we have a mass percent, we can assume 100 grams total. All right, and if we do that, that will get us our kind of jumping off point, because if we know that we have 100 grams total, then we have 37.5 grams of our HCl. All right, so let's start with that part of it, and let's say, okay, it says first calculate the concentration of hydrochloric acid. All right, so let's say that we have 37.5 grams of HCl in 100 grams of our solution total. All right, now, the reason that I did that, right, assumption, was now I can use the density, because the density is for an entire solution. So the density of this is that it is 1.00 grams of solution per 1 milliliters. All right, now what we can do then is we can convert that into liters, where we have 1,000 milliliters for every 1 liter. And finally, we're going to get this to say, okay, let's see where we're at here. Oh, my liters are still okay. My liters are there. let's say my milliliters have canceled, my grams of solution have canceled. I have grams of HCl per liter, but I need molarity. I need moles per liter. So let's convert this into moles. 1 mole of HCl happens to weigh 36.46 grams. So we can now say, all right, I have moles of HCl per liter, and we get this to be 10.3 molar solution. All right, now it also wants us to find the pH. So the pH of this is equal to the negative log of our H plus, which is the negative log of 10.3. And so we get that to be negative 1.013. And remember, yes, negative pH is okay. You're not going to see it very often, but it can occur. It is all right to have that. All right, the next part of our problem asks, what is the pH of 0.175 liters of the same solution? Right, and that's answered down here on the bottom. But just think about it. If you had a bottle of, say, 3 molar hydrochloric acid, and you poured it out into a beaker, and then you walked back over to your lab bench to use it, it's still 3 molar hydrochloric acid, right? Yeah, you have less volume, but you also are going to have less solute dissolved in it. And it's going to be at the same ratio. So you're not going to change the volume by just pouring some of it out, right? You're not going to change the molarity at all. Now you could change that by diluting it, but we didn't do that. All we did was pour some into a different container. So that's going to be the same. Next, let's do sample problem 18.3. All right, now if you've noticed, right, you probably haven't yet, but we are going to work a ton of sample problems throughout this chapter because there's a lot of different ways to think about acids and bases, and I want us to see them 100 different ways so that once you guys start working problems as well, you'll hopefully have seen a lot of these different types of problems worked. Here we're going to find all 4, right? And so again, once we know one of them, we can find the other 3. Now we have 4.68 grams of sodium hydroxide. Okay, so I'm going to start with my 4.68 grams of sodium hydroxide. I need to find, right, the moles of sodium hydroxide so that I can find the molarity of our solution. So we're going to take this, we're going to say 1 mole of sodium hydroxide for every, all right, sodium hydroxide weighs 40.0 grams. And I need the moles of hydroxide, so 1 mole of hydroxide comes from that for every 1 mole of sodium hydroxide, right? Because there's 1 hydroxide and a sodium hydroxide. And we're going to end up with 0.117 moles of hydroxide. If I want the concentration of OH, we're going to do moles per liter. So 0.117 moles of hydroxide. And we have the volume was given to us in the problem. 635 milliliters, so we need that to be in liters, 0.635 liters. And we have 0.184 molar. All right, now we have molarity of hydroxide. So that is our OH, right? That's one of our 4 pieces of information. Now we can find the other 3, right? We can do the pOH. That's the negative log of that. So the negative log of 0.184 is going to be 0.735. All right, next I'm going to find the pH. The pH is going to be equal to 14 minus the pOH. So 14 minus 0.735, and we're going to end up with 13.26. And then lastly, right, my last one I'm going to do is the H plus concentration, which is the antilog, negative, or 10 to the negative pH, which is negative 13.26. So we're going to end up with the H plus concentration being our 5.5 times 10 to the minus 14th molar. All right, so again, once we found one piece, we could use those two equations to plug stuff in and find any of the other unknowns that we were looking for. Well, another sample problem. Here, notice that this one at the top says in-depth. That just means that I'm going to kind of work you through what my thought process was for each step along the way, and I'll number them. Not all of them are in-depth, but some of them throughout this chapter are going to say in-depth on them to kind of get us going with what I'm going through as we do everything. So here we have, what is the pH of a solution by mixing 235 mils of sodium hydroxide, and we're given the pH of it, and some strontium hydroxide, and we're given the pH of that. And that is important when we work this. And we're going to see another sample problem soon, but notice that we're given the pH of both of these things. All right, so it says, since we're dealing with bases, right, let's go ahead and work with finding our OH concentration and then the pOH. All right, so from our sodium hydroxide, okay, the pOH is equal to 14 minus the 11.57, and that's going to be 2.43. So our OH concentration is going to be equal to 10 to the minus 2.43, and we get 0.0037 molar. From our strontium hydroxide, we're going to do the same thing. All right, so we have 14 minus 12.09, which is 1.91. And so we can find the OH concentration of this one as well. And that's going to be 0.012 molar. All right, now it says from that information, we want to determine the number of moles of OH that each one of our bases provides. So let's do this now for NaOH. Okay, we're going to do from each one of our bases. So I'm going to start with that one. So we've got our 235 milliliters, which is 0.235 liters. Hopefully we're really good at doing that conversion because we're going to go from liters to milliliters or vice versa a lot. All right, we've got our liters of that. Okay, then we're going to multiply that by the molarity, our 0.0037 moles per liter. And that is equal to 8.7 times 10 to the minus 4th moles of hydroxide. All right, now we're going to do the same thing for our strontium hydroxide. And so in that case, we have 0.316 liters. We have 0.012 moles per liter. And we get 3.8 times 10 to the minus 3rd moles of hydroxide. Okay, that is the number of moles that is from each one of them. All right, now I want you guys to note that even though, right, you're sitting there and you're like, well, strontium hydroxide has these two hydroxides in it. Shouldn't we take that into account? In this case, we don't, because it's already been accounted for because we're dealing with pH. And thus, then we're dealing with pOH, which then gave us the OH concentration. If we're dealing with it in a different way, another view from this, which we're going to do as a sample problem right after we're done with this one, then yes, we would have to take that into account. But this one we don't. So just notice because of that, it's already factored in. All right, let's finish up the problem here as we go on to our next slide. Well, in part 2 of the problem, or in part 2 of my in-depth working it through, we found the number of moles from each one of our bases. Now we're going to find the total number of moles by taking the sum of those two values. So we have our 8.7 times 10 to the minus 4th from our sodium hydroxide. And we have our 3.8 times 10 to the minus 3rd from the strontium hydroxide. And so we get then 4.67 times 10 to the minus 3rd moles of hydroxide total when we mix these two together. Now we're going to find the hydroxide concentration by dividing the total volume, right, by the total volume that we have in our liters. So we want the OH is going to be the moles of hydroxide, which is our 4.67 times 10 to the minus third moles. We're going to divide that by the total volume, right? We mix two solutions together. And so when we mix these two solutions together, then we have a total volume of them. And so we had our 0.235 liters and our 0.316 liters. So we then end up with the molarity of OH is 0.0085. Finally, we can use this to solve for the pOH and then the pH, which is what we wanted in the very end. So the pOH is our negative log of the OH, which is our 0.0085, which is going to be 2.07. So the pH is 14 minus that, and that's going to equal then 11.93. Woo, we finally got there. Okay, as I said in our previous sample problem, right, we could ignore the fact that we had OH2 from our strontium hydroxide because we were given pHs and that had already taken that into account. But what if we don't take that into account, right? This is going to have us basically do the same problem, but we have to do it by taking into account that we're going to get two OHs from each strontium hydroxide. So we're going to find the number of moles of OH from each, first and foremost. So the OH from sodium hydroxide is, all right, we have 1.16 moles per liter of sodium hydroxide times its volume, 0.316 liters. And we have 1 mole of hydroxide for every 1 mole of NaOH. And so we're going to end up with 0.2726 moles of hydroxide from that. All right, now we're going to do the hydroxide from the strontium hydroxide. Same equation, but we're going to do 2.30 moles per liter. We have where's my volume for that one? Oops. This one should have been 0.235. This one's the 0.316. My math is still okay up there. I just put in the wrong value. All right, we have 1 mole of 2 moles of hydroxide for every 1 mole of strontium hydroxide here. And so we're going to get this to be 1.454 moles of OH. All right, so now, right, total number of moles divided by total volume is going to give us our hydroxide ion concentration. So we're going to have our 0.2726 plus 1.454 divided by, all right, our 0.235 plus 0.316. And so our OH concentration is 3.13 molar. And now we can find the, all right, this case I'm going to do it where I'm going to find the H plus concentration from that. And the H plus concentration from that is going to be 3.19 times 10 to the minus 15th. And so the pH is going to be the negative log of that, which is going to be 14.50. All right, so make sure that you saw how I got there from the OH concentration. Do it whichever steps that you like the best. Just wanted to get us to our final answer there. The top part of this was the more important stuff of showing that that is the case where we did need to take the strontium hydroxide breaking apart into 2 hydroxides into account. All right, in our next podcast, we are going to finally start talking a little bit more about equilibria of these things.